Good afternoon, ladies and gentlemen. This academic session could have been called Bits and Pieces of Aeronomy. Our colleagues have presented numerous topics, studies, projects, which are the parts that together form the contribution of our institute to the science branch that is called Aeronomy. This presentation is called Bits and Pieces for Aeronomy. While over the past 50 years, our scientists gathered bits and pieces to solve the aeronomical puzzle, a team of engineers and IT specialists went along all the way. From the very first day the Institute was founded in 1964 till today, supporting the scientists, implementing their ideas, offering them platforms and infrastructure to do their measurements and calculations, transforming their requirements in real instrumentation. If we say bits, we mean bits like in transmitting megabits of data to the ground, or bytes, like in terabytes of storage capacity on disk or in the cloud. If we say pieces, we mean mechanical parts, electrical components, computers, or servers. Vijay Kumar, an Indian roboticist and professor at the School of Engineering and Applied Sciences of the University of Pennsylvania, made, probably on a Blue Monday, the following statement. Without engineers and IT guys, science is just philosophy. We added the wing smiley ourselves because quotes are just quotes. The truth for some, a lie for others, and often something in between. But since we are engineers and IT guys, we admit that we do fancy the expression. Don't you agree that life would be less exciting without technology? That life would be less efficient without technology? That life would be less practical without technology? And that life would be much more tiring without technology? And what is science other than life itself? Professor Kumar was born only 2 years before the Belgian Institute for Space Aeronomy was created. We assume that the founding fathers of our institute were not acquainted with his famous quote. Nevertheless, they were convinced that this young science, they called Aeronomy, could not grow without reaching the hand to technology. But as much as science needs technology, technology also needs science. For it is the playground where inventions are made and the future is shaped. Science, engineering, and information technology at our institute go hand in hand.
We are happy to say that this fundamental idea has not changed over the past half-century. Engineering and IT played and still do play a prominent role in the history and strategy of our institute. For over 4 decades, engineering and IT were part of one department, the Department of Applied Aeronomy. All the credits for the evolution, the expansion, and the impact of engineering and IT on the Institute go to 3 engineers who led this department from an era where electronic tubes were on the verge of disappearance, transistors had only just emerged, computers were huge and merely had the capacity of a modern hand calculator. And they led us into the 21st century. Dirk Vriemhout, until he left the Institute in 1978 to become Belgium's first astronaut. Eddy Neefs, until he retired in 2007. And Carlos Lippens, until he retired in 2008, never ceased to introduce state-of-the-art engineering and information technologies in the Institute and put them at the service of our scientists. Only some 10 years ago, it was decided to have separate services for engineering and IT. mostly due to the fact that the IT needs of the scientists have boomed spectacularly. Today, engineering and IT support projects that can be ground-based, air or space-borne, and are active in a wide range of domains such as mechanical design, software development, ground support equipment, electronics design, onboard software, mechanical manufacturing, prototyping and testing of equipment, operations, project management, web design, high-performance computing, data storage, networking, e-administration, infrastructure management, interconnectivity, personal computing, and IT consultancy.
But how can we demonstrate better what are the tasks and domains of competence of engineering and IT than by showing you the past and ongoing achievements of our teams? Allow us to take you on a very short journey through 50 years of designing, manufacturing, assembling, testing, and using of scientific instrumentation and information technology. We are sure we will encounter on the way some of the projects mentioned in the earlier talks of our colleagues. By the time ESRO, the European Space Research Organization, the precursor of ESA, puts the first Skylark and Centaur sounding rockets in the atmosphere and the first satellites in space, also the Institute becomes active in developing experiments. In the early years, electronics for scientific instrumentation consisted of discrete components: transistors, hybrid operational amplifiers, resistors, condensers. Programming of equipment was based on mechanically driven timers. Data was recorded by means of pen recorders and paper. The engineering team at BIRA built payloads for rockets, measuring, amongst others, the UV radiation, and for the very first balloons at the end of the 60s, carrying optical and mass spectrometers into the stratosphere up to between 20 and 50 kilometers and ranging in weight between 10 and 300 kilograms.
In those years, the complex mathematical calculations and data processing needed by the scientists for the physical and chemical modeling were done by calculators. These were no machines, but persons doing the calculations with pencil, paper, and slide rulers. The concept of high-end computing was introduced quite rapidly. Computers such as an IBM 1800, which was only programmable by electronics experts, an HP 2100 mini computer with a huge 32 kilobyte memory, an HP 1000 mini computer, which was later used as a ground support equipment for 2 shuttle missions, and the UNIVAC mainframe all did duty at our institute. Initially, there was no IT yet. The BISA engineers were the pioneers of these emerging computing activities. Our flesh and blood calculators started using the electronics calculators, and the first computers programming them in BASIC and Fortran. With the signing of the ESA Convention, and hence the official start of the European Space Agency in 1975, Europe gave form to its dream to follow Russia and the United States in the conquest of space and stepped into a decade of wonder years. In our institute, engineering and IT marched on, following closely the fast evolutions in microelectronics and computing. Bigger mainframes replaced their precursors and offered more calculating power to the scientists. But also data storage changed dramatically. Data and computer programs were initially stored on punch cards, later on paper tapes, then on tape reels, and finally on hard drives. In the beginning, as big as refrigerators and with a mind-boggling storage capacity of 1 megabyte. Slowly, also the personal computers started taking over part of the work of the centralized mainframes.
Balloon campaigns remained one of the key activities in engineering, sometimes launching up to 4 instruments per year. stabilized platforms were introduced with the possibility to accurately point the line of sight of the instrument. Little by little, integrated circuits and logic devices, such as flip-flops, logic gates, found applications as instrumentation grew more complex, and digital remote communication became a necessity. Heavy lead batteries were replaced by much smaller and reliable nickel-cadmium batteries and later by lithium batteries. Although the capabilities of the first microprocessors were negligible compared to what processors can perform today, the new techniques were introduced and applied from the very beginning. One of the biggest achievements of engineering in this period was the participation in 3 instruments that were placed on board NASA's Spacelab 1 module in 1983. The Institute had important contributions in the ALAE instrument and the grill spectrometer. The 3rd instrument was SolSpec, which was built in collaboration with the Service d'Aeronomy in Paris, now LATMOS, an institute that has always been closely linked to ours. The SolSpec instrument would later be rebuilt and reflown several times. On Eureka in 1992, and on 3 Atlas missions in 92, 93, and 94. But also the grill spectrometer would fly again on Atlas 1 in 1992, together with Dirk Vriemout, and on the Russian space station Mir in 1994. For Belgium, but also for our institute, the next decade is undoubtedly marked by the fact that one of its pioneers and engineers, Dirk Vriemout, became the first Belgian astronaut in history when he flew aboard mission STS-45 of Space Shuttle Atlantis in March 1992. Vriemout had left the institute, but research and engineering work didn't stop. On the contrary, Aeronomy boomed when international consciousness regarding the alarming change of our climate awoke. Balloon flights went on, lifting now mass spectrometers of over 500 kilograms into the stratosphere, built in-house by engineers and technicians from the mechanical workshop and the electronics lab. The most eye-catching accomplishment was without any doubt the fact that the Institute placed 2 of its instruments on board Eureka, ESA's European retrievable carrier that was launched and deployed in 1992 and retrieved in 1993. Besides SolSpec, also ORA, which stands for Occultation Radiometer, was on board. The Institute played an important role in the scientific conception and consequent data analysis, but it was also strongly involved in the building and testing of this instrument.
And from the IT side, business as usual, meaning increasing year after year the capabilities, the computing power, and the storage capacities, in order to deal with the experimental data that by now is captured electronically. This goes hand in hand with a fundamental shift in the research methodology, introducing automated data processing and numerical simulations. Inside the engineering department, IT becomes more and more a self-contained service, delivering dedicated support to the users of the developing IT infrastructure. The period of 1995 to 2005 is a decade that underlines ESA's resolve to conquer the solar system with the launches of Mars Express in 2003, Rosetta in 2004, and Venus Express in 2005. Isn't it amazing that a small institute as ours is prominently present in all 3 of these missions, with important hardware contributions, and becoming like that also an important player in planetary and cometary aeronomy. However, this time frame started really catastrophically with the failure of the Russian Mars mission Mars 96 that crashed a few minutes after its launch in 96. With Marenf and SPICAM-S, the Institute had 2 instruments on board. SPICAM-S was an optic spectrometer designed in-house, and its loss was a real pity. But it would leave a legacy, The heritage of SPICAM-S would be used to build, together with the French Service d'Aeronomy, the SPICAM Light instrument on Mars Express, and, consequently, the SPICAF Soir instrument on Venus Express. Two highly successful missions and two highly successful instruments that today are still active.
Contrary to ground-based instrumentation, building instruments for space is something a small engineering team cannot do on its own. Intensive collaboration was set up with the Belgian industry, such as Verhaert for SPICAM-S, now Kinetic, and OIP sensor systems for SWAR. Typical of this period is the tendency to embark more and more intelligence on board the scientific instruments, making them quite versatile measuring benches in space. This was made possible by the further evolution in electronics, especially with the development of performant space-qualified microcontrollers, microprocessors, and field-programmable gate arrays. Very recently, Rosetta became headline news again, 10 years after its launch. When last August it finally arrived at Comet CJ, the first amazing measurements were performed from the orbiter. And 2 weeks ago, as you all know, Philae landed on the comet. One of the instruments on board Rosetta is DFMS. It is a double-focusing mass spectrometer that is part of the Rosina suite. The Institute played a major role in building the instrument. It developed the detector of DFMS, a linear electron detector array, together with IMEC, and the readout electronics of the detector, together with OIP.
In the test lab and during flight, more and more workstations are used as ground support equipment for instruments. The development of ground support software has gone hand in hand with instrument developments in the team. But also in the central computer rooms for the Space Bowl, investments go on with the installation of new generations of supercomputers, such as the Great Jedi and the SGI Origin, as well as the first centralized mass storage systems, all at the service of the new demanding numerical modeling algorithms. These large-scale systems and infrastructures are all procured and operated jointly with our colleagues of the Royal Meteorological Institute and the Royal Observatory under the flag Amabel. Meanwhile, the advent of the Internet accelerated the pace of IT development, and for the first time, the IT infrastructure becomes critical to the day-to-day functioning of the Institute. By the year 2000, nobody can live without email, Google & Co, and the by now very personal PC. As a landmark in the last decade, we have, of course, chosen the celebration of the 50th anniversary of our institute, and we have called this period the adult years. Half a century of science in Aeronomy and half a century of accompanying engineering and IT work have made us a full-grown player in the international scientific community.
The engineering team is working with modern CAD tools for mechanical designing and with the latest electronic design software tools. Our engineers are and will be more than ever involved in ground-based instrumentation and space applications. Our hardware can be located nearby in a field, on a rooftop, in a tree. It can be installed at the most exotic locations at the other side of the world. Contributing to ground instruments with mechanical and electrical hardware, supporting them with operation and automatization is a non-negligible part of our day-to-day work. But our hardware can also be embarked on board of mini-satellites, like the Energetic Particle Telescope, EPT, on board Proba-V, launched in 2013, in which the Institute contributed with mechanical hardware. Or Altius, a spectral imager under development, to be launched also on a Proba platform. It can be on a Pico satellite, like Picasso, carrying miniaturized scientific equipment.
It can also be on one of ESA's large-size missions, such as the Trace Gas Orbiter, the first segment of the ExoMars program, to be launched in January of 2016. With the Nomad instrument, the Institute again has an important technical contribution. Electronics boards, onboard software, ground support equipment, mechanical parts, and a high-tech flipping mirror mechanism, which is one of the specialties of the team. Today, our institute stores more than 300 terabytes of scientific data. That is roughly the equivalent of 60,000 compact discs. In the future, novel solutions will have to be found to continue storing and processing these increasing amounts of data, a real challenge. The actual computing power available to the Institute has increased by a factor of 1 trillion with respect to the early days, and we are on the verge of increasing this by another order of magnitude. This is, however, completely in line with Moore's law and futurist Kurzweil's thesis, which says the following: the accelerating pace of change and the exponential growth in computing power will lead to a singularity. Moore predicts that by the next year, a single computer will exist that surpasses the brain power of a mouse. By 2023, that of a human, and by 2045, that of all mankind. In anticipation of this glorious day, when we can all retire and leave research and development to the computers and the robots, the IT department tries to use simple gray matter to automate routine tasks, be they administrative or for research, to manage the increasingly complex IT infrastructure and its services, and the ever more creative ways in which our scientists use the new technologies.
Speaking about technology, we would like to mention also that besides the engineering and IT service, the Institute houses another important pole of technological competence. The Belgian User Support and Operations Center offers to scientists services ranging from engineering support over knowledge and project management to mission operations. They played, for example, a primary role in the operations of Solspec on the Solar platform, or of EPT on ProbaV, and will contribute also to the Nomad operations on ExoMars. We would like to take advantage also of this occasion to say a word about yet another service in our institute. The service has not been in the spotlights today, although without it, this event and all other events that were organized at the occasion of our 50th anniversary would not have been possible. Managing the website of the Institute, editing the yearly reports, interfacing with the press, organizing appearances in the media, and many more. The communication service of the Institute brings, through educational programs and public outreach at numerous events, our scientific and technical achievements under the attention of society. Although the fields of application of engineering, IT, and communication may be diverse, our three services and the BIUSOC have a common ground. We try to contribute, each in our own way, to better science, or a world where science can be performed in the best of conditions. As the title on this last slide says, for sure, our services deliver very concrete bits and pieces for Aeronomy. But we proudly think that all the things we do are just as well bits and pieces of Aeronomy. We thank you for your attention.